Hey, physics, this is Mr. Nunez coming at you from my present, but your past, even though you're now watching it in my future, but your present? Hmm. Well, anyway, today we're going to be talking about periodic motion. I hope you guys are able to make it through this video. And if you have any questions, feel free to reach out to me. I'm in New Mexico, and hopefully, I will be able to get to your messages in between my meetings. Um, Periodic motion, otherwise known as simple harmonic motion, is really important for what we're going to talk about for the rest of the year. Um, Hopefully, by the end of this video, you'll understand periodic motion, especially amplitude, frequency, and period, and then you'll better understand the graphs related to an object's periodic motion, otherwise known as waves. So let's get into it. You're here. I'm absent. It's so you're going to be doing your periodic motion overview. Make sure that you watch this video in its entirety. You're taking the notes in your OneNote in 5.01, and that you complete all of the practice and submit it. I will be grading it for completion, so make sure it is done so you get that easy grade in the grade book. But more importantly, so that you learn something and you're ready for me on Monday. So I want to start with where we've been. So far in this class, we've only looked at one thing, and that is what we call linear motion. So an object that's moving, in a straight line, or even when we were talking about stuff that was moving curved, we could basically treat it as motion horizontally and motion vertically, which is just a combination of two different linear motions. And so if we wanted to, talk about this person's motion on their bike, we would call some starting point, position 0, and we know that their velocity is moving to the right. And we could basically plot their positions over time. And that's what this graph would end up looking like is, if we were to start a stopwatch at a certain point, after, 0.1 seconds, they're here. After 0.2, they're here, and so on. And so this has been pretty simple because, relative to where the object starts, to that initial position, they're always moving away from it. And even if they turn around and come back, we can plot that as well on our graph. Periodic motion is interesting because it's defined as repeated movement through an equilibrium or starting point. And so there's a really good example right here on your screen where you've got this ball of yarn that's swinging back and forth. And so this middle point is what we would call the equilibrium point. Okay, the equilibrium point. And you can think of this as where if I hadn't moved the yarn ball to begin with, it would just be hanging in that one point. And so I tip it, and then it's just going to swing back and forth. You've probably seen those in some of those old-timey clocks, or, in the movies where they try to mesmerize you by swinging something in front of you, which doesn't work. Different things like that. This is different from our linear motion because instead of the object constantly moving one way, it's going back and forth through where it started. So the graph starts to look a little bit funky, and we'll see that in just a little bit. Now, one thing I want to be sure of that you hear early on is you'll hear this motion referred to as simple harmonic motion, hence the meme at the beginning of class. Or you may also hear it referred to as oscillating motion, okay? And oscillations are just kind of vibrations back and forth. And so if you hear simple harmonic, oscillating, periodic motion, all of those mean the exact same thing. And so before we get into any of the vocab about it, I want to show you some of the different periodic motion that exists, okay? Because the pendulum, which we'll talk about in a second, is a really simple example. But you can also think about if you had something attached to a spring, you've got this equilibrium point right here, and it's constantly moving back and forth between one point, up here, and one point down here. I guess that would mean the equilibrium is somewhere here in the middle. And so it's just oscillating back and forth between those points, which makes it periodic motion because it's going through that equilibrium point. This one's kind of different for us to think about, but if you move around a circle constantly, that's also considered periodic motion. So if we were to call this the starting point or the equilibrium point, we can see that the object, although it's moving around the circle, constantly goes through that equilibrium it goes to its furthest point, it comes back through the equilibrium, and it just keeps on doing that. We also see this very commonly in waves, okay? So we often think of waves because we are simple humans. We think of waves as moving this way. But if you were to focus just on one point, say this point right here in the middle of the screen, in fact, if I put a line over it, you can see that one point on the line is constantly going back and forth through this equilibrium point, that point right in the middle of its motion. So it goes up to a maximum point, then it goes down to its minimum point, and so the equilibrium point is right here in the middle. So in all of these cases, you have an object that is moving back and forth through an equilibrium point, which is the definition of periodic, simple harmonic, or oscillating motion. And so in physics, we have a few different ways that we describe periodic motion. These are three big vocab words that we're going to talk about today. You have what's called the amplitude of the motion, the frequency of the motion, and what's very closely related to frequency is the period of the motion. Okay, so amplitude is basically describing, if we were to measure, say here's our equilibrium, what is the furthest distance from equilibrium that an object can be? And so you'll see that the furthest distance on the left of my pendulum is equal to the furthest distance on the right. And so we would say the amplitude is the measurement from the equilibrium to its maximum point. And the amplitude here on the left is going to be equal to the amplitude on the right. Okay, so those maximum points are going to be the same, but in good physics terms, we would call one side positive and the other side negative. So it's going to this maximum point on the positive side, goes through the equilibrium and to the maximum point on the negative side, and then it just kind of goes back and forth between those. Frequency is a word you've probably heard before. Frequency measures how many times it goes back and forth to where it started per second. Okay, so let's say I set a stopwatch and I watched it go from its maximum point here. This is where we start, and I start my stopwatch, it goes to the other side, and then it comes back, and I stop it. And let's say it does that in 1 second. Well, then we would say that the frequency is one time, or one cycle, we call that, per 1 second. And so we would say that this object has a frequency of 1. And oftentimes you'll see this as 1 over seconds. That would be the unit for it. But most commonly, and the same thing as 1 over seconds, is hertz, which is capital H, lowercase z, named after the scientist that kind of theorized how to describe this kind of motion. So hertz, Hz, is how we measure frequency, which is how many times it cycles back and forth. Let's say, it went back and forth 2 times in 1 second. Then its new frequency would be 2 cycles in 1 second. So we would say that it has a frequency of 2 hertz. Period is just the time it takes to complete 1 cycle. Okay, so frequency is just 1 second. Period is how many cycles or how many seconds for 1 cycle. So frequency is 1 second. Period is 1 cycle. So again, let's start with our first one. Let's say it only goes back and forth 1 time in 1 second. Well, then for period, we would say that it takes 1 second per 1 cycle, which would mean that it has a period of 1 second. We kind of ignore cycles because cycles is just a way of counting, and so that's not really a unit. So you'll never see cycles show up in the unit. But if it completed 2 cycles in 1 second, so it had a frequency of 2 hertz, that would mean that it took 1 second for 2 cycles, which would mean that it has a period of 0.5 seconds, or 1 divided by 2. And so there is a relationship that exists between period and frequency, where period and frequency is just like flipping the fraction. So you'll notice 1 second is 1 hertz. So 1 over 1, flip it, it's still 1 over 1. But 0.5 seconds is the same thing as 2 hertz. So 1 over 2, flip it, 2 over 1. Okay, so I know that this can be confusing. You may want to pause and rewatch that description one more time. Periods, though, the key here is that seconds is in the numerator, and you're saying how many times does it go back and forth in 1 second. And frequency is how long does it take for it to complete 1 cycle. Frequency is how many cycles does it take in 1 second. So you may need to watch this a couple times to get it. But the big thing to know is frequency and period. You can just flip them back and forth. So let's look at a few GIFs that explain this, each of these vocabulary terms. For this one, I don't want you to worry about the wavelength and the phase. We're going to talk about those later. For right now, I just want you to think about the amplitude. So you can see as the amplitude is decreased, the distance from the maximum to the equilibrium changes. So if it's higher, then it has a high amplitude. If it's lower, then it's a low amplitude. Okay. The most important thing, though, is that you always measure from the max to the equilibrium. Okay. Amplitude is not all the way from the top to all the way to the bottom. It's just from the top to the equilibrium, or alternatively from the bottom to the equilibrium. Because remember, a few slides ago, we talked about how the amplitude from the max and the positive is equal to the amplitude from the max and the negative. So if we were to look at this with a spring oscillator, this is a pretty good example. So you can see that our spring on the right is barely moving. So we would say that this thing has a low amplitude because it is not moving very far. On the other hand, if you look at the spring that's moving on the left-hand side of your screen, you can see it has a much bigger amplitude. It moves much further from that equilibrium point. So again, I think we said the equilibrium was somewhere, like right around here, right? And so it's barely moving its maximum points to that center line. And remember, don't make the mistake. It's not from top to bottom. It's from top to middle. Versus this one, it goes all the way up here, all the way down here. And so if we measure that distance to the middle, it is much greater than the spring oscillator on your right. And so because this is just a measurement of position, we're still going to measure amplitude in meters or centimeters. Period would be like, again, focus on this yellow dot on the left. We're basically focusing on what this one dot does. So it goes up to its maximum point here, and then its maximum point there. And what we're just measuring, I missed that maximum point. What we're just measuring is how many seconds does it take for it to get back to where it started. So it would be like start the stopwatch, stop the stopwatch, start, stop. If we were to measure that time, that would be the period of this wave. So you can see the little yellow part going from the very top down and then back to the very top. And the time it takes for it to do that is considered a period. Frequency, like we said, is flipped. So now you'll see that if we were to measure how many times it cycled within 1 second, the frequency goes up. So this was measuring the time it takes for it to go back to where it started. This is measuring how many times it goes back to where it started in 1 second. So as we cram more and more waves into 1 second, you get a higher and higher frequency as shown by this number right here, right? So we're cramming more of these oscillations into 1 second. So the number of cycles per second is increasing, okay? And then alternatively, if we were to take it and then stretch it back out, there would be fewer cycles per second, so you would see the frequency go down. You've probably been familiar with waves for a lot longer than you think, okay? When we listen to sounds, we are basically listening to this complex interplay of amplitude and frequency. So when we're talking about sound, amplitude is the volume, and frequency or period is the tone. So I'm going to show you an example of this using an online tone generator. It's going to just play a musical note, and I'm going to warn you right now, this tone's going to be pretty loud. So I'm going to give you a second. Turn down the volume on your device. So take a second, turn the volume down pretty low because it's going to be a little loud. Okay. So I'm going to hit play. So if I'm going to mess with the amplitude, that's like me changing the volume. If I change the frequency, notice this is measured in hertz. And I'll stop that because it's probably giving you a headache. So this kind of vocabulary absolutely shows up in sound, and so I want to be sure that you're aware of that as well. So what will we as teachers ask you to do with this? You're going to have to do just a little bit of math with it. And as long as you understand that relationship between period and frequency, it's fairly simple. So let's say a spring oscillates back and forth. So we're basically talking about this situation right here. And let's say we had our stopwatch with us, and we saw that it went back to where it started 10 times in 2 seconds. So 10 oscillations or 10 cycles in 2 seconds. So question 1 is frequency. And in frequency, seconds are in the denominator. So that means if I want to calculate frequency, which is just the lowercase f, then I'm going to put 10 cycles on the top divided by 2 seconds on the bottom to get a frequency of 5 hertz. Period, we can think of as how many seconds it takes per cycle. So in the case of period, remember, seconds is on the top of our fraction. So we're going to say it's 2 seconds per 10 oscillations, or it has a period of 0.2 seconds, okay? Notice the fractions are simply flipped. So when you're going between frequency and period, all you have to do is flip those fractions. So let's get back to waves for a second. When we're talking about waves, there's going to be a lot of this, okay? It's just the movement of energy through what we call a medium, okay? So a medium is just the thing the wave is moving through. The thing the wave is moving through. And we're going to look at a few examples of that. And so this is not to be confused with the stuff we've seen before, okay? That was periodic motion. Now we're thinking about actual waves, okay? So something that moves up and then down and then up and then down. And we have some additional vocabulary that we're going to have to use, but most importantly, we're going to need to be able to describe it on a graph. So the first thing that's really important is understanding wavelength. And wavelength has this Greek symbol. The name of the Greek symbol is lambda, L-A-M-D-E, and it looks like kind of an upside down Y. Okay, so you got like one long edge, like a backslash, that's got a little extra leg sticking out. Okay. The important thing about wavelengths is that you're always measuring between two of the same points. Okay. So if I wanted to measure the wavelength starting here, I need to measure when it gets back to that point after one complete motion. So this would be one wavelength. I could do the same exact thing on the bottom, and it would be equal to the wavelength on the top. So those two values are equal. Here's where everybody makes a mistake. If I wanted to measure a wavelength here, a lot of students would say, I just need to measure to here. Well, if we look at that, this line is nowhere close to the length of this line or this line, which should give away right away, oh, that's not how I measure wavelength. And that's true, because if we think about the wavelength measured from the top, it has to go all the way to the bottom and then back. Or if it's on the bottom, it has to go all the way to the top and then back. So if we wanted to start at the equilibrium point, it has gone down, but it hasn't gone all the way back up. So it's got to go all the way back up, come back to the equilibrium, and then this represents one full wavelength. Okay, so all of these are equal to each other. Amplitude, again, is very simple. Amplitude is just the measurement from the equilibrium point to the maximum point. So this would be the amplitude. You can also measure to the bottom maximum, just like we talked about with our pendulum. In order for us to tell the frequency, we would need to know how many waves happened per second. So that's the same exact vocabulary. And for period, it's just the opposite of that, how many seconds it takes per wave. There's a couple other vocabulary words, though, when we're looking at a wave as opposed to something going through periodic motion, and that is the peaks, otherwise known as the crests, and that's just a name that we give to the maximum positive point. And then at the bottom, we call these troughs. A trough is the like container of food that farm animals eat out of. So think like donkeys and stuff. They're those like big giant containers that sit on the ground. So they kind of have that V shape or that U shape. So that's why we call them troughs. You may also hear them referred to as valleys. So you've got your peaks and crests at the top. You've got your troughs or valleys at the bottom. And then again, that middle point is what we call the equilibrium point. Okay, so those are the vocab words that we're going to be using to describe the waves. So let's look at this in the context of a real problem. Let's say you have this wave that's moving back and forth. As you can see by our little GIF here, the wavelength is constantly measuring from peak to peak. We know we could also measure it from valley to valley, or we could measure it from one point going all the way up, back down, and then it would be like right about here. Okay. The amplitude would be how high, let's say this is the equilibrium point. The amplitude is the measurement from the top to that equilibrium point or from the bottom to that equilibrium point. Okay, so amplitude. And again, in order for us to calculate the frequency or the period, we would have to have a stopwatch that told us the time. Because we don't have a stopwatch, we can't do that here. Let's talk about sound again. Okay. Oh, actually, before that, sorry. One other thing I want to mention. So medium, earlier I said, is the thing that the wave is moving through. So in this case, you've got this object over here that's wiggling what looks to be like, I don't know, maybe a chain or a string or something. And as it's wiggling that chain, we would say that the medium, the thing that the wave is moving through, is the chain itself. So this gets kind of confusing then, because when we think about sound actually happens in the air molecules. So in a speaker, you've probably seen them before. There are these little devices that essentially move. You may have seen them in cars that have a loud thumping bass, and they've that black circular disc that pumps out. What that black circular disc is doing is it's literally pushing the air, and it pushes the air in every direction. But if we were to just look at one slice of that air, whenever the speaker pushes, it's actually forcing those air molecules together. And then some air molecules bump into some other air molecules, which then bump into some other air molecules. And as that energy travels through the air, it goes into our ears, which also there's an ear space in there. And it's literally tapping up against your eardrum, which then sends signals to your brain. And we have evolved to take those signals from the air and convert it into what we interpret as sound. So literally, you listening to my voice right now, if you're listening in headphones, there's a small gap of air between your headphone and your eardrum. And so as my voice is talking, it is vibrating the air. That air is then vibrating your eardrum, and then your brain is converting that into sound that you can interpret. So if you've ever heard the phrase, you can't scream in space, or no one can hear you in space, that's true. Now, you would have to be outside of a spacesuit, because we know spacesuits have air in them, which is why our astronauts can breathe. But if somehow you were able to take off your spacesuit in space and not instantly freeze because of the sub-zero temperatures, or bake to death from the radiation, and you could attempt to scream, nothing would be able to hear you because there's basically no air in space to carry that energy. And so space is going to become really important later in this unit as we start to talk about special waves that can move through space. But the thing to understand here is, although this is a sound wave, the medium is actually measured, or is actually the air, because the air is the thing that the wave moves through. Which, remember, is our definition for medium. Okay? So if you were to measure the distance between those air molecules being pushed, you would get the wavelength, right? So you could measure from valley to valley or from peak to peak. And so you should see that that represents one wavelength. The amplitude, again, the volume, is not something you can easily see if you were to look at the air molecules, but if you were to look at it on a graph, that amplitude, or the volume, would be the measurement from the center to the peak. And again, just like we saw with, or heard with that tone generator, as the frequency goes up, the pitch gets higher, those waves get smashed together. And as the frequency gets lower, then those waves get spread apart, and so we hear a lower tone as a result. So let's look at what you're going to have to do in class, since I know that's the important part. We'll give you something like a graph that has a wave on it, and then ask you a bunch of questions about it. So question 1 here, given this wave, what is the wavelength of the wave? Hopefully you remember wavelength is measured either from peak to peak, from valley to valley, or if you wanted to measure it from the equilibrium point, it has to go all the way up, down, and back to where it started. So if I do it that way, it becomes very clear on this graph. This is a position of 0. This is a position of 10. So the wavelength of the wave is 10, and there's no units on this graph, but let's just call it meters. The amplitude is measuring from the center to the top, or from the center to the bottom. And so I can see here that this is 7, and the same thing is true from the top. It's also 7. So we would say that the amplitude is 7. Again, let's just call it meters. And without a stopwatch, you can't know the frequency or the period. And so you'll get a question like, if 6 waves pass in 12 seconds, what's the frequency? And what you need to remember is frequency means that seconds is in the bottom of the fraction. So that means to calculate my frequency, I'm going to put 6 waves over 12 seconds, which is 0.5 hertz. And I could even ask you, what is the period of the wave? And remember, period means that seconds are in the numerator. So that would be 12 seconds per 6 waves, or 2 seconds. So it would take 2 seconds for 1 wave to pass. And that is it. That is an intro to periodic motion and waves. So what do you need to do at this point? You need to complete the rest of the notes, which is numbers 1, 3, 4, 6, and 7. If you were following along with me, you should already have 2 and 5 done. Here's the thing though, I want this on a sheet of paper that you can put into your OneNote, because there's just too much copy pasting going on in my class. So put it on a sheet of paper, take a photo with your phone, put it on your OneNote, and that is it. If you guys have any questions, or if any of this was too confusing for you, feel free to send me a chat. I'll do my absolute best to get back to you, assuming that I'm able. Otherwise, just hang tight until Monday, and I will see you then. Thanks, y'all. I'll see you on Monday.